An aromatic hydrocarbon or arene is a hydrocarbon with sigma bonds and delocalized pi electrons between carbon atoms forming rings. The term aromatic was assigned before the physical mechanism determining aromaticity was discovered. The term was coined as such simply because many of the compounds have a sweet, pleasant odor. The configuration of 6 carbon atoms in aromatic compounds is known as a benzene ring, after the simplest possible such hydrocarbon, benzene. Aromatic hydrocarbons can be monocyclic or polycyclic. Some non-benzene-based compounds called heteroarenes, which follow Huckel's rule, are also called aromatic compounds. In these compounds, at least one carbon atom is replaced by one of the heteroatoms, oxygen, nitrogen, or sulfur. Examples of non-benzene compounds with aromatic properties are furan, a heterocyclic compound with a 5-membered ring that includes a single oxygen atom, and pyridine, a heterocyclic compound with a 6-membered ring containing 1 nitrogen atom. Benzene ring model. Benzene C6H6 is the simplest aromatic hydrocarbon, and it was the first one named as such. The nature of its bonding was first recognized by Auguste Kekule in the 19th century. Each carbon atom in the hexagonal cycle has 4 electrons to share. 1 goes to the hydrogen atom, and 1 each to the 2 neighboring carbons. This leaves 1 electron to share with one of the same 2 neighboring carbon atoms, thus creating a double bond with 1 carbon and leaving a single bond with the other, which is why the benzene molecule is drawn with alternating single and double bonds around the hexagon. The structure is alternatively illustrated as a circle around the inside of the ring to show 6 electrons floating around in delocalized molecular orbitals the size of the ring itself. This depiction represents the equivalent nature of the 6 carbon-carbon bonds, all of bond order 1.5. The equivalency is explained by resonance forms. The electrons are visualized as floating above and below the ring with the electromagnetic fields they generate acting to keep the ring flat. General properties of aromatic hydrocarbons: they display aromaticity. The carbon-hydrogen ratio is high. They burn with a sooty yellow flame because of the high carbon-hydrogen ratio. They undergo electrophilic substitution reactions and nucleophilic aromatic substitutions. The circle symbol for aromaticity was introduced by Sir Robert Robinson and his student James Armitt in 1925, and popularized starting in 1959 by the Morrison and Amp Boyd textbook on organic chemistry. The proper use of the symbol is debated. It is used to describe any cyclic pi system in some publications, or only those pi systems that obey Huckel's rule in others. Jensen argues that, in line with Robinson's original proposal, the use of the circle symbol should be limited to monocyclic 6-pi electron systems. In this way, the circle symbol for a 6-center 6-electron bond can be compared to the Y symbol for a 3-center 2-electron bond. RNA synthesis. A reaction that forms an RNA compound from an unsaturated or partially unsaturated cyclic precursor is simply called an aromatization. Many laboratory methods exist for the organic synthesis of arenes from non-RNA precursors. Many methods rely on cycloaddition reactions. Alkane trimerization describes the cyclization of 3 alkanes. In the DOTS reaction, an alkane, carbon monoxide and a chromium carbene complex are the reactants. Diels-Alder reactions of alkenes with pyronocyclopentadienone with expulsion of carbon dioxide or carbon monoxide also form RNA compounds. In Bergman cyclization, aromatization, the reactants are an arene plus a hydrogen donor. Another set of methods is the aromatization of cyclohexanes and other aliphatic rings. Reagents are catalysts used in hydrogenation such as platinum, palladium and nickel, quinones and the elements sulfur and selenium. RNA reactions. Arenes are reactants in many organic reactions. Aromatic substitution. In aromatic substitution, one substituent on the RNA ring, usually hydrogen, is replaced by another substituent. The two main types are electrophilic aromatic substitution, when the active reagent is an electrophile, and nucleophilic aromatic substitution, when the reagent is a nucleophile. In radical nucleophilic aromatic substitution, the active reagent is a radical. An example of electrophilic aromatic substitution is the nitration of salicylic acid. Coupling reactions. In coupling reactions, a metal catalyses a coupling between two formal radical fragments. Common coupling reactions with arenes result in the formation of new carbon-carbon bonds, e.g. alkylarenes, vinylarenes, biraryls, new carbon-nitrogen bonds and new carbon-oxygen bonds. An example is the direct arylation of perfluorobenzenes. Hydrogenation of arenes creates saturated rings. The compound 1-naphthol is completely reduced to a mixture of decalonol isomers. The compound resorcinol, hydrogenated with raney nickel in presence of aqueous sodium hydroxide, forms an enolate which is alkylated with methyl iodide 2,2-methyl-1,3-cyclohexandione. Cycloaddition reaction are not common. Unusual thermal deals. Alder reactivity of arenes can be found in the Wagner-Jauregg reaction. Other photochemical cycloaddition reactions with alkenes occur through excimers. Benzene and derivatives of benzene. Benzene derivatives have from 1 to 6 substituents attached to the central benzene core. Examples of benzene compounds with just one substituent are phenol, which carries a hydroxyl group, and toluene with a methyl group. When there is more than one substituent present on the ring, the spatial relationship becomes important, for which the RNA substitution patterns ortho, meta, and para are devised. For example, 3 isomers exist for cresol because the methyl group and the hydroxyl group can be placed next to each other, 1 position removed from each other, or 2 positions removed from each other. Xylanol has 2 methyl groups in addition to the hydroxyl group, and, for this structure, 6 isomers exist. Representative RNA compounds. The RNA ring has an ability to stabilize charges. This is seen in, for example, phenol, which is acidic at the hydroxyl, since a charge on this oxygen is partially delocalized into the benzene ring. Polycyclic aromatic hydrocarbons. Polycyclic aromatic hydrocarbons are aromatic hydrocarbons that consist of fused aromatic rings and do not contain heteroatoms or carry substituents. Naphthalene is the simplest example of a PAR. PAHs occur in oil, coal, and tar deposits, and are produced as byproducts of fuel burning. As pollutants, they are of concern because some compounds have been identified as carcinogenic, mutagenic, and teratogenic. PAHs are also found in cooked foods. Studies have shown that high levels of PAHs are found, for example, in meat cooked at high temperatures such as grilling or barbecuing, and in smoked fish. They are also found in the interstellar medium, in comets, and in meteorites, and are a candidate molecule to act as a basis for the earliest forms of life. In graphene, the PAR motif is extended to large 2D sheets.